Okay, so the key to finding this volume is to look at this hemisphere minus the drilled out cylinder from the top. Okay, so what does it look like from the top? Because that's going to give us the region of integration. All right, so you have a radius 4 circle, right? And that is the circumference of that, the circle, which is a boundary, the bottom boundary of this cylinder, solid. And then we have a radius 1 hole drilled out. Okay, so this is 1 and this is 4. So the region all over which we are integrating this solid is actually this area between the two circles, right? Looking at it from the top. So that's going to be, how do you define the bounds for the double integrals? Well, obviously, let's see, theta is between 0 and 2 pi, right? And let me adjust my pen a little bit. And as far as r is concerned, it goes until 4, but it doesn't start at 0, right? Because this part is excluded. And that's really a nice feature of this coordinate system, because I said removed. It's not 0, it's 1, right? Because this point is 1. And so that's the region R of integration. Now, what are we integrating? Well, for each R and theta you pick here, in this point, let's say this point here corresponds to this point, we are to integrate the length of this segment from the bottom to where it touches the hemisphere. Now, this hemisphere, as you know, has the equation x squared plus y squared plus z squared is what? The radius is 4, so this is 16, right? But we need this in terms of not x and y, but r and theta. Well, fortunately, this is r squared, right? So basically, this is saying z squared is 16 minus r squared, or z is, and of course, this is the top hemisphere, not the bottom hemisphere. So this is the square root, the positive square root of 16 minus r squared. That would be our integrand. And once you've figured these facts out, the volume will be rather simple to define or to calculate. V is the integral from 0 to 2 pi, and another integral sign from not 0, 1 to 4, and then you put the integrand, right? And then what's the rest of it? It's supposed to be the dA part. dA is represented by r, dr, d theta. Where did this r come from? Well, that itself is dA, if you remember, in the polar coordinates. So that is what we have to integrate. Now, this square root may make things complicated, but thanks to this r, right? Because of this r, we can actually do a nice substitution. You can do 16 minus r squared. Let that be u, and then du is negative 2r dr. With this substitution, of course, I need let's use red. I need negative 2 right here. That would be negative 2r dr, right? So that would make that into a du. If I can just put that in there, can I do that? Well, sort of, right? You can make this enter, or you can just put this negative 2 in here, as long as you divide everything by negative 2 outside. All right, so then, and then of course we have to make some adjustment here. Theta doesn't change, but r does, right? Instead of this r, let's see, when r is 1, okay? So these have to be changed. When r is 1, this is 15. When r is 4, you have 16 minus 4 squared, that's 0. So this one goes from 15 to 0. Kind of odd because, this number is bigger than the bottom one, the top one. But that's okay. And then we have, what is that? U to the 1/2. That's the square root of 16 minus r squared. And then we have du, right? This whole thing is du, and then d theta. Once you get to this point, I think you're fine. All right, what do you have after this? Well, let's see. This is going to be u and then 3/2 and then 2/3, right? And then you just integrate this from 15 to 0. Now, this is something you can do, but it is kind of annoying to have this number here less than the bottom number. So what I'm going to do is, it's a little trick. I can switch the sign of this if I switch these, right? So that just makes, you don't have to do it this way, but it's a little nicer or less annoying as far as I'm concerned. All right, so you can go ahead and do this. And let's see, with this substitution, we are about to get this done. Let's cancel the 1/2. You get 1/3, still an integral, right? And then this part will be, well, what's 15 to the 2/3? That's going to be 15 times the square root of 15, right? It's a cube root, it's a square root of 15 raised to the 3rd power. And then minus 0, which I'm not going to write. Okay, so then that, of course, you can cancel out. Let's go ahead and just write it this way. And then 3, and then 2 pi. Of course, this and this will cancel. And the answer looks like 10 times the square root of 15 times pi. And that, my friend, is the answer to that question, which is the volume of this drilled out hemisphere. Okay, now I'm just going to give you a one optional example, just because you know, it may be fairly complicated to learn how to do double integrals in different coordinate systems, such as the polar coordinate. And so let's look at this one more thing. Maybe I'm going to add another page for this. All right, so this bonus question is to find the volume of the parallel, let's see, we should call this a paraboloid. Okay, so it's a circular paraboloid capped off by the horizontal plane z is equal to 4. And so, and this is very similar to one of those problems you have to do for your homework. Okay, we are to find the volume of this cup, the paraboloid, under the surface z is equal to 4, or the plane z is equal to 4. Okay, now you can project it down here. Oh, I didn't give you the equation of this. This is z is equal to x squared plus y squared. So again, the usual circular paraboloid, right? If you project it down here, you can see that the projection onto the xy plane is the circle of radius 2, right? Because again, 2 squared plus 2 squared, 2 squared plus 0 squared is 4, and so on. Okay, so let's try to find the volume of this. Now, how do you do that? Well, again, z is equal to, now you can recognize x squared plus y squared, that's just r squared. And so you may think that's what we are going to integrate. Well, it's fairly close, okay, but let's try to figure this out. The region of integration, that's this circle here, right? The region is going to be defined as, well, that's simple. Theta goes from 0 to 2 pi, right? And then how about r? R goes from 0 to 2. Okay, so it's rather simple. So the volume is going to be the integral 0 to 2 pi, integral 0 to 2. And then we have to have r dr d theta. Now, what's the integrand? It turns out it's not that, okay? Why is it not r squared? Well, if you do r squared, that's what you're saying is you measure this length from 0 to r squared. So that's going to be from this point to that point, right? From a point on the xy plane to the point where it touches the paraboloid. So that would be everything outside of this cup, like this, right? That's why you can't use r squared for this particular problem. If you're looking for inside, you have to measure for each, okay, again, for each theta and r, so that's going to be right here, you know, some particular point r theta. You measure the length from this point, which is on the r square surface, to the z value of 4. So that would be 4 minus r squared. That's what we have to integrate. Okay, Just be aware of that. And I will make one more comment about this in just a few minutes after this problem is solved. All right, once you set this up, it's not too bad. 4r minus r cubed, that's what you will be integrating in the end. All right, so that would be 2r squared minus 1/4 r to the 4th. Oh, and then you evaluate this from 0 and 0 to 2. Okay, let's go ahead and do this. So the outside doesn't change. Inside becomes 2 times 2 times 2, that's 8, minus 16 divided by 4, that's 4. All right, so this is 4 times 2 pi, and of course that's 8 pi. And that is the answer to this question, all right? So the volume of this cup, circular paraboloid, capped off by z equals 4, turns out to be 8 pi, okay? Now let's say, and this is a bonus part of the bonus question. Let's say you forgot this thing, okay? And you just entered this, z is equal to r squared, which is the length, well, not the length, the volume of what's outside of this cup over the cylinder of radius 2, okay? So here, let me go ahead and draw this like that. You know, now we're trying to find the volume of this outside here. It looks much smaller, right? Well, think about this. So this will be just like before, okay? But instead of 4 minus r squared, you'll just have r squared, right? That's the length of these vertical lines from here, 0 to where it touches the paraboloid, which is where z is r squared. So you will set up this integral. You know, again, if you may be doing this erroneously, like, yeah, you didn't realize you're trying to find the volume of the thing outside as opposed to the inside. But a curious thing happens, as I discovered while I was grading Calculus 3 exams years ago. All right, so what do you get? It's 1/4 r to the 4th, going from 0 to 2, right? You don't have this complicated two-term, not too complicated, but you don't have this two-term function to integrate, so it's kind of easy here. Well, this part is 1/4 times 2 to the 4th power, that's 16 divided by 4, that's 4. Okay, so it turns out you still get the same answer. Maybe it's surprising that the outside volume is the same as the inside volume when you have this circular paraboloid, x squared plus y squared. And it turns out there's nothing magical about z equals 4, okay? And it turns out that this volume inside and the volume outside and inside of this surrounding cylinder turns out to be equal to each other regardless of this horizontal cutoff plane. Z can be anything, and you can prove that that's going to be true. Now remember, this will be always a square of this number, right? Because when you project it down here, you get the square root of this number. But given that constraint, the outside volume will always be equal to the inside. Kind of a surprising fact. And if you want to, as a bonus to the bonus question, you can actually work it out. Let this number be r and z going to r squared or something. Okay, so I think I have done a lot of exercises for you, showing you different examples, demonstrating problem solving. Now it's your turn to get on with your homework, learn your double integrals really well, because the next thing that's coming is, as you guessed it, triple integrals using various coordinate systems. All right, so hope you have fun. Take care. I'll see you later.